Okay, so just to show you a little bit more about convolutions, I wanted to show you this Mathematica notebook that I have online here. So I'll post this for you to download and play with if you want. It's pretty neat. I usually use this for a course I teach with Laplace transforms. So my integrals start from 0 and go up to t, as opposed to being an integral over the whole line or something. But let's see. So let's start with just this sort of shark fin function that I've created here. Just as an example to see what does it look like when I look at t minus tau and then shift for different versions of tau. So we've flipped it, so it goes horizontally, and then for different versions of tau, it's shifted by a certain amount, right? And so this is the idea that you should think of about what's happening when we do a convolution. So if I make the unit interval characteristic function here, so it's equal to 1 on the unit interval and 0 otherwise, then let's look at what happens if we convolve against this function here. So my shark fin starts off, I've got a picture of it here just so you can remember what the baseline image looks like, but I've got the shark fin translated and flipped off to the left, and then as we integrate over tau, it goes across and across and across, and then boom, here it comes, passing through the window and going back down again, like so. And so what is the convolution? The convolution is the area of that shaded region. So for small values of t, it's very small, and then it gets bigger and bigger and bigger, boom, so we've got a lot of area, so the convolution would have a large value right here, and then it would drop off and get smaller again. Okay, let's do something which is a little bit more numerically precise, and I'll take a copy of that unit step function and convolve it with itself. Okay, and so here are two unit step functions, sorry, not unit step functions, characteristic functions of the unit interval. Now, one of them has been flipped and translated. Now, the flipping does nothing because it's a symmetric function from left to right, but the translation means that one of them is off to the left. And so as I bring it along, let's see what happens. So here comes the other characteristic function. So tau is negative, but it's increasing. As soon as tau gets to t gets to positive, rather, now there's an overlap, right? And so when there's an overlap, now we're looking at the area of that common space, which is this blue region right here. The value of this area is represented by the height of this dot. All right. So as they overlap more and more, the common area increases. The dot goes up, and when they overlap fully right around here, boom, and then at this point it starts to slide out the other side, and the intersection becomes smaller, and as a consequence the value of the area is decreasing, so the dot is going down. So it goes down like this. So the convolution, if I look at the graph of the convolution of these two functions, these two characteristic functions of the unit interval that are sliding around here, the resulting convolution looks like this tent function right here. So it's interesting to notice that we went from two discontinuous functions, right? They got jump discontinuities. And then the convolution of them is now a continuous function. It's not differentiable because it's got cusps at these points here, but it's still continuous. Okay, so there we go. All right, now what happens if I take two of those tent functions and convolve them together with each other? So we'll get something that looks like this sort of bell curve. Now this is not a Gaussian, it's a different kind of bell curve. It's actually, it's a spline. But let's see, so now we've got two of those tent functions, and as we bring them together right here, here we have, so this shaded region here, the area of this, well, the upper bound is the product of this downward slanting function here and this upward slanting function here, right? So these are all values between 0 and 1. So let me dial it over to like here. So now right at the apex right here where they're meeting, this is 1/2 times 1/2. So there's the yellow one has value 1/2, the blue one has value 1/2. Multiplied together give you 1/4. So the height of the product is here, right here at 1/4. So remember, because this is the blue region here is the area of f times g, or rather f times the flip of g, the translated flip. So again, when we start off here, the area of the blue region is very small, so the dot is very low. But as we overlap more and more, the dot rises, indicating that the area is getting bigger and bigger, and then boom, right here, that's the maximum overlap. So if I took that tent function and squared it, you can see it would give you this sort of slightly rounded version. It's still pointy and slightly rounded. But now 1 times 1 is equal to 1, so the blue region reaches all the way up to 1. And then as they overlap less and less, we have the same thing sweeping out on the backside. And so now we've taken two functions which are not differentiable, and we've convolved them together, and we've got something which actually is differentiable. Okay. And so here's one more example, something slightly less symmetric. So this is a decaying exponential function. So, whoa, what happened here? Hold on. There we go, that's what I was expecting. Okay. So I'm going to take this exponential function here and convolve it against itself, and we're going to see this resulting sort of bulbous tail thing going here. So as the exponential function comes in, notice that the one of these is e to the x, and the other one is a shifted version of e to the minus x. And so e to the x times e to the minus x, those two parts are going to cancel each other out, and you're just going to be left with the shift part. So as a consequence, you get a horizontal flat line. So in other words, the pointwise product of the e to the x and the shifted e to the minus x is a constant function. And so you get some rectangle. And the area of that rectangle gets bigger and bigger as it gets wider. It gets bigger up to some point, and then the fact that it's getting shorter overtakes the width, and it starts to get flatter and flatter and flatter, and we drift off again. Okay, so I'm going to post this on Canvas, and you can download it and play with it as you like.